All right, so let's take a look at the ideas that we find in section 5.1. Um, the, we actually have two kind of ideas, and so we're going to have two different videos. So the first idea just is a discussion of what we call sigma notation. All right, so sigma notation. And this is maybe something you've seen, but of course sigma notation is referring to the Greek letter sigma, okay? And so basically, if here's an example of something in sigma notation, right? So the sigma of from I equals 1 to, we'll put 4 of I. And what this means is this right here is the formula. And into this formula, so this is real simple, this is just the formula I. It could be an entire equation, you know, I squared minus 2I plus 7. And these values tell you what you plug in. So we're going to start by plugging in 1 and get out a result. And we're going to plug in all the numbers from 1 to 4. So we'll plug in a 1, a 2, a 3, and a 4 into this formula. And then the sigma tells us to add those up. That's what sigma notation is. All right? It's going to be adding up some things. And we've got the formula to generate the things that we add up. And we've got the limits, 1 to 4. So if I plug in a 1, I get a 1. If I plug in a 2, I get a 2. If I plug in a 3, I get a 3. If I plug in a 4, I get a 4. And so then I add those up. That's what the sigma notation is telling me to do. And I get the value of 10. All right. So let's see another one. Sigma. And we usually use i's, but it could be anything, right? So it could be like n equals, and we'll say 3 to 7 of n squared minus 2n. And so that's telling me start by plugging in a 3. So when you plug 3 into the formula, you get 9 minus 2, or 9 minus 6, which is 3. Now plug in a 4, a 5, a 6, and a 7. So let's plug in a 4. 16 minus 8 is 8. Plug in a 5. 25 minus 10 is 15. Plug in a 6. 36 minus 12 is 24. And we're adding these all up. And then finally plug in a 7. 49 minus 14 is 35. And so we would need to add those up. So 2640 or 2650, 85. All right. And there it is. So this is what sigma notation is. Okay, you're adding up a series of values, and that's what we like. Now, there are some common things that we add up quite often. So let's go back to this formula that we started with. Of just, well, we'll use from I equals 1 to n of I. So this, if you look at what this is asking us, we plug in a 1, we plug in a 2, we plug in a 3, we plug in a 4, and we keep plugging in things until we get up to n. And so basically this is the formula that says, hey, add up all of the numbers from 1 to n, right? And so that's the notation. And there it is, right? So we do that, okay? We do that quite often in what is coming up. Another thing that we do quite often is add up the first n perfect squares, right? So that's what that formula would look like. So that's telling us to do 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. So all the way up to, we'll write it like this, n minus 1 squared plus n squared. So that's telling us to add up all of the first n perfect squares. We do that quite often. Now, here's the deal. We do these things so often that this would be a pain, right? And n is large. In what we do, n is going to be large. In fact, it's going to go to infinity. So we're going to add up the first, 100,000 integers. And I don't want to plug those into my calculator. Well, it turns out for this simple example, for this simple process, we actually have a formula that gives us the sum. And the formula is this: n times n plus 1 over 2. And you can look in the book to see how that's derived. It's very clever. But that's a very famous formula. So if I want to add up the first, let's say, I'd like to add up, the first 1,000 integers, right? So there's my formula. I recognize it because my formula is just I. And it's 1 plus 2 plus dot, 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 all the way up to 999 plus 1,000, right? If I wanted to add those up, I could add them up, one at a time, or I can use my formula, which says it'll just be 1,000 times 1,001 divided by 2, all right? And so what's that, 500, oops, that's something like 550,000 or something like that. Let's check that out real quick. Or sorry, not quite that much. Yeah, so it's 500,000. 500, right? And so that's nice. I don't have to actually type in, all the integers from 1 to 1,000. I can just use my formula. Okay, so that's clever. That's a handy thing to have when we're doing these summations. Well, you might ask, well, is there an easy way to do this one, right? To do the sum of the first n squareds? And the answer is yes. We do have a formula. Let me see if I can put it in over here. No, I'm gonna actually write it down here. So here we go. So if I want to add up, if I'm adding up the first n perfect squares, okay, then, so that's 1 squared plus 2 squared plus dot, 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 plus, let's see, n minus 1 squared plus n squared, right? Well, that is equal to, we have a formula, n times n plus 1 times 2n plus 1 all over 6. Okay? So if I want to add up the first, 100 squares, I could just plug 100 into this formula right here, and I've got the answer. So that's real handy. Lastly, we'll just give you the formula. We have a nice neat formula for adding up the first n cubes. Okay? So of course that's 1 cubed plus 2 cubed plus dot, 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 all the way up to n cubed, right? Well, the formula is actually this: n squared times n plus 1 squared over 4. All right? And so you'll use those formulas to calculate some values. And so you can combine these, right? So those are simple formulas, but maybe I need to, maybe somebody says, well, what is the sum from I equals 1 to 52 of I plus... Well, before we do that, I want to mention one other thing. Let's do this. So we have one other little property that we can use here that's helpful, and it is this. If I'm adding up the sum, well, we'll write a couple more. The first n constants. So if I have a formula that looks like that, all right, where c is just a constant, right? So in other words, that's just c plus c n times. So if I'm just adding up a bunch of constants, then the answer is just going to be n times c, right? Because you're just adding up c multiple times. Now, finally, here's the last thing on the right. If I have a constant times some function, I equals 1 to n, and a sub I is some function, some formula involving I. And this is basically just a coefficient, okay, in front of that formula. So like 6i or 7i or 7 or 12i squared, right? Basically the rule is this. I can factor that constant out from the summation. So really all I'm then doing is C times the sum of the first n values into the A sub I formula, right? So why does that matter? Well, let me tell you why that matters. Because we can now do this, right? Suppose I want to add up the first 20 entries from this formula, first 20 values from this formula. 3i squared minus 7i. Well, I can break this down like this. Oops, let's do this. All right, so basically I can rewrite it and break it down like this. As 3 times the sum I equals 1 to 20 of I squared. Okay, minus 7 times the sum I equals 1 to 20 of I. Right? So I pulled those coefficients out, right? And then I just had this term, and I can just subtract them individually. So it's almost like I'm distributing this summation notation. And so look at this. The nice thing is this formula was complicated, right? And we didn't have a formula for it, right? But since I broke it up, I can write it like this. 7 times I squared from I equals 1 to 20, right? So the sum of the first I squared perfect squares, first 20 perfect squares, which is 20 using our formula times 21 times 41 all over 6 minus, I'm sorry, why do I have the 7 there? This is not the 7. This is the 3, because that's the coefficient in front of the I squared. So 3, bam, right there. And then the sum of the first 20 perfect squares is right there. That's just using our formula. And then we're going to do minus 7 times the sum of the first i's. So minus 7 times the first 20, the sum of the first 20 integers using our formula is 20 times 21 over 2. And so if I work all that out, then I will have this complicated sum just by being able to break it up into these simpler sums. And so the result we get is 7140. All right. So we start by with these three with those basic formulas, and then we have then we can combine them. We have some basic properties, but using that that idea, you're able to find much more complicated summation values of summations.